Washington State University. Go Cougs!
Yeah, thank you so much, Aurora. So I hope all of you can hear me fine. Okay, good. I am a faculty in computer science here. I do research in parallel programming, so I thought we should talk about this, and I was very pleased to actually hear that this was being organized for all the engineering and sciences and whoever is interested across the campus, and that's great. So this will be a very introductory, basic, level parallel programming class. We will cover some concepts just to introduce you to some of the fundamental techniques and the parallel programming models and so on. However, for anything to do with hands-on exercises, we will essentially use OpenMP multi-threading. Okay, so this is basically shared memory or whatever code you want to run on a single node using multiple cores, multi-core programming. Okay. So stop me if you have any questions. I'll be glad to answer them. And so as Aurora pointed out, you should have downloaded the slides from here. I will basically drive the slides from here, but the slides are for your offline reference. You will also find some references. If you're new to C programming, you can use that, but I'm guessing that you either be programming in C or Fortran mostly, or Python is fine too. For this session, however, I'll just use C as an example, and many of the OpenMP pragmas and directives you should be able to carry over. And to get a bit more understanding of all the API for OpenMP multi-threading, here is one of the authoritative websites, which will be a very useful reference. Okay. So which computer should I use? Okay, this one. All right, so let's run through the slides on this side, and we will use the command console whenever we want to look at code. Okay, so we all are used to programming on serial computers. Serial computers or sequential computers are basically the von Neumann architecture, where essentially you have one CPU, which is your processing unit, and there is a memory attached to it, and in the middle there is some cache, which is for faster access of data, and then there is a disk, right? So we are used to actually programming in serial computing. The challenge is you basically can execute one instruction at a time, right? That's what makes it serial or sequential. So why we need to write parallel programs? A, because we have multi-core architectures, right? We should be able to exploit them and use them, take advantage of them, so that we generate parallelism. And the motivation from the application side should be first to speed up the computations, right? Make the computation faster. There's also a more probably noble cause, I should say, of trying to achieve better precision or higher quality of your computation, right? In many applications, you are limited by how much you can do in a certain amount of time, so you settle for perhaps a lower quality at the end by basically coarsening the computation. But if you have access to larger resources, you might be able to go at a finer level of computation and be able to achieve possibly a better precision at the output. So these are all possible ways to actually take advantage of parallelism, right? So people also talk about scaling up the data size in addition to scaling up the processor size. Scaling up data size means what used to solve, is now limited to how much ever memory you have. Now, if you have many such nodes, then you can take advantage of the aggregate memory across all those nodes and be able to scale up the problem size, right, that you can solve. Or you can, instead of simulating possibly a million, maybe 100,000 atom system, perhaps you can simulate something of the order of a million atom system, something like that, right? And especially that's relevant in today's world where there's all this talk about big data and so on, right? So the question is, there are multiple advantages and benefits to writing parallel program, but how do we write it? That's the next question, right? So simple ways to approach it can be classified into these two categories. The first category is task parallelism. So essentially you look at your code and say, hey, this function does not give any output variable that's needed for these other function. So perhaps I can run these two functions independently on two different cores, right? So that's task parallelism. You can typically do this when there is no dependency between these two tasks or across these tasks that are running concurrently, right? The other notion, which is actually what we are more used to, it's easier to think about, is the data parallelism. So the parallelism is not in the task, but in the data that we are trying to process, right? So if you are trying to, let's say, process some data which is on the file system, and let's say there are 1,000 files on the file system, and if you have 100 processors to work on it, then you can take the 1,000 files, break it up into chunks or blocks of 10 each, right? And give the batch of 10 to each of the 100 processors. This is data parallelism, right? And it's easy to, whenever we farm out tasks, or whenever we farm out the data and chop it into blocks and say independently compute, that's data parallelism. And so here is a simple example that essentially ties both of them. So here, let's say there is a professor, some exam, 300 exams basically, and to grade, and 15 questions within each exam. And let's say there are 3 TAs. So data parallelism is take the 300 exams and there are 3 TAs, divide them up into equal pieces, right? 100 exams each TA. The other approach is the task parallelism, where you don't divide up the exams, but you divide up the questions. There are 15 questions in each exam. So we say, hey, questions 1 through 5 goes to TA1, 6 through 10 goes to TA2, and 11 through 15 goes to TA3. Now here we'll have to be slightly careful on how we distribute it, right? So actually it might so happen that questions 1 through 5 might be the light, like simple questions, right? So it's easier to grade or faster to grade them. And as the number increases, perhaps 11 through 15 takes more time to grade, right? So the TA3 unfortunately has to spend more time than the other 2 TAs, right? So we don't want to create such load imbalance. Wherever possible, we should try to achieve a load balance. So these are some of the optimization constraints that we would like to consider when we are designing parallel algorithms, right? So maybe looking at the question, you might think, 1 to 7, the amount of work that the TA needs to do to grade the first 7 questions is roughly the same as whatever it takes to grade the last 4 questions, right? If you have that understanding, then you can divide the questions up accordingly, right? In addition, the questions here, if in some sense, the same question is being graded by the TA. So it actually helps in some way, right? And so it gives a consistent view at the end of the grading. However, the same exam is being graded by 3 different TAs, and so the scales could be different. That's where communication coordination is required to make sure it's consistent across, right? So coordination is a very, very key concept when it comes to parallel programming. It comes in different flavors. One is these different processing elements, they talk to one another, exchange information on the fly on what pieces of data they are computing as they are computing. They say, okay, I have a checkpoint here, I should relay this information to some other processor so that it knows that this has been computed, so that other processor doesn't have to recompute that, things like that, right? So there has to be a communication. The other thing is keeping the load that's balanced. And also synchronization is a key concept. Synchronization essentially means that the processors need to understand, or at least try to get a global view of what other processors are doing at any given point of time. So a simple example would be if 3 processors are trying to write on to the same variable at the same time, right? So obviously they may corrupt the data because they are doing concurrent write on the same data variable. So then they should essentially try to coordinate their efforts in such a way that one of them does it first, leaves out, and the second one does it next, and so on. So it needs to be ordered, serialized at that manner. So that's an example of a synchronization. So we'll look at all these flavors over this 2-hour period, the workshop. So what we'll be doing is essentially we will try to understand how to extract parallelism from simple programs. We have to first understand where the parallelism is, right, in order to highlight what parts of the code can be parallelized and what part of the code cannot be parallelized. And then we'll use C language, and we'll use OpenMP, and we'll use this for multi-threading. for shared memory machines. I will talk about shared memory machines and so on, but multi-threading is different from multi-processing. Okay, so threads and process are two different concepts, so I just want to emphasize that. A process basically means that it's what the operating system allocates as a single address space. A process is essentially, when you start your code, it basically spawns a new process. Okay, within a process you can have multiple threads executing. So multi-threading is within a single process, which means all the threads can see the same memory, the same address space.